So if we have this data and we need an equation to find to give the best fit of the given data set, we can do many things, but simple thing is a linear regression. We have this y equal mx plus b, the good old equation, and we have this data x and y, which x is independent and the y is dependent data. They're both one-dimensional. And then we have these parameters. We have slope and the intercept, y-intercept. Now we need to find, and we're going to call this slope and intercept as parameters. So how do we find the best parameter? Or how do you even judge what we found is it good or not? So we can just give like a random guess of mn, and as you've seen here, and it's a poor guess, but we have to judge how it performs. How we do is we given x, we have some sort of y value, right, the prediction value, and we get the difference between the prediction and then the real data set. So the distance between the two, which we'll call the residual, which is the predicted output or y minus the actual y. And if we square them, because of some distance are going to be negative, and then if we just add them all up, we have the sum squares the residuals. And that number will give us how much far off or we are to the actual data and represent the actual data. And we want to minimize this sum of squared residual. So we have like similar the arc, mean, theta. So this is just the sum of squared means, squared residual, and then we want what it is saying, like give me the theta that minimize this value. Assuming that we already know the b, we can search for optimal m. So if we go from here to, and then we slowly go like that, we're gonna get something like that, and this is representing the squared sum of residuals, the error rate. And we clearly see a minimum point, and which is something like that. So this makes sense. But what if we don't know the y-intercept, and we have two parameters to search over, and obviously, and this is called grid search, and obviously it's going to take a lot of effort. And so how do we make this more efficient, right? So we have this linear regression. So we get some value of m, which is the initial random guess, and then we evaluate what the error is, and we get basically error derivative, the gradient, and then we see the slope is tilting to the left, and we know we can move to the left, and then we repeat it again. It's like, and then we get the gradient again, and then always still leaning toward left, and then we continue to a point where the gradient, the error is minimized. So sometimes we need to reformulate the linear regression, so we have one-dimensional for both, but we need to. We're going to augment the independent variable to 2D. So we just put like one for each column for the sake of augmentation. And the reason we did this is because the theta parameter MB is 1/2 array matrix, and we apparently need to match these two for us to be able to do like metrics, and we do that, and that's what we kind of simplify into here. And then so we have data, model, and cost, the slope. We do some like chain rules to simplify this, and we're gonna eventually get the 2 times the predicted data minus the actual data, so that's the residual, and then times x, which is the independent data. And we can go like they eventually go to the minimum, but a lot faster than the grid search. And how we can speed it up is we can increase the step size, how much it moves every time it goes to other side. But it would be bad if it keep missing the minimum because the step size is too big. So to use this for neural data, we have some stimulus over here, and there's spikes as well, which is the resulting output. And we have this step size for the time. And they are like so they have like obviously a nonlinear relationship, and we're also assuming so we have the previous model, and then we're gonna convert it into this gamma, which is equal to e to the power of theta x for here, and then this y, the residual, not residual, the predicted plus the error. This is the residual, it's the actual data, and the actual data is going to be Poisson's times gamma. And gamma is just it's really representing the probability of firing, so firing rate, in other words. So now we have this maximum likelihood estimation, finding the theta that minimizes the error between the prediction and data, but it's just a different framing. Instead of minimizing the error, we're maximizing the likelihood. By the way, the reason why we did this, the J, this term, the reason why we do this is so that we can use this gradient, or that we know the derivative of this J, and then we can use it for our gradient descent for the LNP model. And that's why we went back to LNP model, and then once you do the math, you get these, and then we have this argument, and then from here we can get this J. We're going to put log over here, and then log kind of cancels out this E, and then so we have only here, and then log, so yt over here, and then log, and then hт over here, and then minus since it was in the bottom, and then log yt, this exclamation mark, and then we can simplify it since gamma is E, so there's that right over here, and then log goes away because it's E, so yt times theta xt, and then minus this is same. And if we take derivative, since we're taking derivative for the theta, this since it doesn't have any theta, it goes away. So we have like pretty much same thing over here, and then derivative over here. And then if you like rearrange it, so we pull out the x and then put the rest over here, we get this form. It looks kind of similar to the what is it similar to? Kind of similar to this one, but yeah. So going back to our biology, so stimulus retina, which is comparable to the LNP, and the responses. So the linear filter is actually a representative of the receptive field. If you just here. So we have this receptive field, and then this is like not active, this is like active zone, etc. And if you just take the cross section, well, like the radius line, and then if you just like draw it, how like it's like active and then repressive, something like that, right? It looks, I mean, if you flip it, it's kind of similar to this linear filter over here. And then point nonlinearity and Poisson's spiking, there's not really a biological representation. If there were to be, it would be something in between the receptive field and then the spiking and everything in between. So this gamma t, which is this arrow over here, what's coming out of the point nonlinearity, could be represented as the e to the power of theta xt. So linear filter, I was confused about the difference between linear filter and nonlinearity. First of all, linear filter, we can see it's quite like linear, like where it's like not smooth, and it's like a piecewise function. It's like we piece together many different linear functions, and nonlinear is just one smooth function. And the reason why I do that is it's just a lot easier to do it that way instead of trying to combine both non-linearity and linearity in one function. Because split it into two different functions, it becomes a lot easier. Also, another different thing is that for linearity, we have some stimulus, and we divide it into like some arbitrary time interval, and then we combine this or average it into some number, and we put it over here, and then we can get some sort of corresponding output over here with the y value, and we put that y value over here, right? But for nonlinearity, so we get one number, and we get precisely get one number, then we get precise corresponding some output from nonlinearity function. So linearity filter takes input where there's like it's really average of this like bunch of stuff, whereas nonlinearity is like precise number, like one precise number. Okay. Sometimes, so this one there's like 15 parameters, and yeah, that's why we do like this complex math, because although our example was only 2, if there was a 15, we can't even imagine the 15th dimension like space. So that's just kind of LNP like summary, and there's that.